Dear students, in the previous modules you have already become familiar about the E1, E2 and EI reactions and how they proceed with the help of their mechanisms. In this module we shall look into the various effects of substrates, leaving group, the solvent polarity on the reactivity in these electrophilic aliphatic substitution reactions. So, here we will focus first on the mechanism of electrophilic aliphatic substitution, that is we will revisit the Sc1, Sc2 and Sci mechanism, and then discuss the effect of each, that is the substrate, leaving group and solvent on these one by one. Dear students, after studying this module, you shall be able to know what are aliphatic electrophilic substitutions, learn the types and mechanisms of aliphatic electrophilic substitution as a recap, identify the factors influencing reactivity of electrophilic aliphatic substitution and evaluate the effect of nature of substrate on electrophilic substitution reactions. And once you have gone through all these details, you shall be able to analyze the effect of reactivity on deciding the mode of electrophilic substitution reaction under a given set of conditions. So, let us begin with recalling that chemical reactions when an electrophile, that is an electron deficient species, displaces an atom or group of atoms in a compound, typically but not always the hydrogen atoms, they are termed as electrophilic substitutions. Broadly, electrophilic substitutions we have already seen and you are aware that they are classified as aromatic electrophilic substitutions and aliphatic electrophilic substitutions. The aliphatic electrophilic substitutions involve reactions at a saturated carbon center, which is sp3 hybridized, and the substitution electrophilic reactions are classified based on molecularity of the reaction. For example, they can be unimolecular, that is Sc1, or bimolecular where they are Sc2 or Sci. So, recalling the mechanism of the various electrophilic aliphatic substitution reactions, first of all let us start with Sc1 mechanism. The unimolecular electrophilic substitution mechanisms are termed as Sc1. These mechanisms, they follow the first order reaction kinetics with respect to the substrate. The Sc1 mechanism involves two steps. The first step is a slow rate determining ionization step, as you can see here, and it leads to the formation of the intermediate carbon ion. And you can see here the Rx is undergoing ionization to give you R minus, which is the carbon ion, and with the removal of X plus. The second step involves the fast combination of electrophile, say Y plus, as you can see here, with this R minus, resulting into the product Ry, which is being represented in this case. Here Y plus can be H plus, Cl plus, Br plus, NO2 plus, R3C plus, etc. like electrophiles. The stereochemical outcome of Sc1 reactions are difficult to predict due to the complicated configuration of carbon ions formed during the first step of ionization, and invariably the products get racemized. This is because the sp3 hybridized carbon atom may take up a pyramidal shape or may acquire a planar structure. The pyramidal carbon ion has been reported to flip analogous to the umbrella effect in amines, and thus both the sides attacks are possible and leads to a racemic mixture. On the other hand, if the carbon ion has a planar structure, then also the attack of electrophile would be possible from both the sides and would lead to a racemization of products. So, if it is a planar, then you can clearly see here that it can attack from this side or this side. So, now you can see here is the mechanism of racemization in Sc1 reactions with planar carbon ions, and you can clearly see here this B will abstract this X plus as the leaving group, and it will result in the ionization and formation of this carbon ion. And this carbon ion, if it is planar, it can be attacked from both the sides. So, attack from this side will lead, the back side of X will lead to inversion, and attack from the same side as the X was earlierly present, then it will lead to retention. So, both the products will be formed, and that is how there is a racemization which is exhibited. As a result, racemization is almost always observed for the products of Sc1 mechanism. Although whether this is caused by planar carbon ions or by oscillating pyramidal carbon ions is not settled, as it may vary from case to case due to the nature of the substrate. The acid or base catalyzed halogenation of aldehydes or ketones is a classical example of Sc1 mechanism. As you can see here, let us take the case of acetone. When it is reacted with base, the base will take out this proton, the alpha hydrogen, and generate this carbon ion, and this carbon ion then attacks on the bromine, taking the Br plus and leaving the Br minus. So, this is the electrophilic aliphatic substitution happening via the Sc1 mechanism. That is, the first step is the formation of carbon ion, and then it will be taking the electrophile. Now, moving to the Sc2 mechanism, the electrophilic substitution biomolecular mechanisms are termed as Sc2 mechanisms. These mechanisms follow the second order kinetics, as their name suggests, with respect to the substrate and the electrophile. The Sc2 reaction mechanism is concerted, that is, proceeds via a single transition state where the old bonds and the newly formed bonds are both present simultaneously, that is, the old bonds are in the process of breaking and the new bonds being formed are in the process of being made. But unlike the SN2 substitution, which always results in inversion of configuration of the reaction center, for Sc2 reactions there are two possible ways of electrophilic attack to the reaction center. The first one is the attack from the front, which is called as Sc2 front, that results in the retention of configuration. As you can see here, when this X, which is the leaving group, and from the same side this carbon will be getting joined to this Y plus, then there is a retention in configuration, and this is a simultaneous concerted process. The second option is the attack of electrophile from the rear or the back side, which is called as Sc2 back, and this obviously will lead to the inversion of configuration, as you can see here. So, this is almost analogous to the SN2 backside attack, but here the carbon, which is the reaction center, will be attacking on Y plus, and as a result the X plus goes away. Majority of second order electrophilic substitutions proceed via retention of configuration, implicating the front side attack resulting from Sc2 front mechanism is more common. For example, when compound was treated with labeled mercuric chloride, the product represented as 2 is produced with 100% retention of configuration, thereby confirming that it is going through the Sc2 front mechanism. So, you can see here this cyclohexyl derivative, when it is reacted with the mercuric chloride, which is labeled, and the star is representing the labeling. So, what we get is this particular group is being replaced with HgCl, and we get this particular product. So, what you can see here is this molecule, which is labeled as first, is undergoing Sc2 with mercuric chloride, and notice that in the product it is Hg is not the unlabeled one as it was in the starting molecule, but it is labeling. So, that is why we can say that this entire group is getting replaced with the labeled Hg and Cl, and we are getting this 100% retention in the configuration because it is the front mechanism. So, we can say that HgCl has attacked from the same side where this is there, and this grows and it is getting replaced with the labeled HgCl. For an electrophilic substitution reaction, evidences for front attack are second order kinetics along with stereochemical retention of configuration. Now moving to the Sci mechanism. The substitution electrophilic internal mechanism is termed as Sci mechanism. So I stands for internal here. These are concerted mechanisms and follow second order kinetics with respect to the substrate and electrophile. In the mechanism, electrophiles with suitably placed functional groups attack the sp3 hybridized substrate from the front, whereby a portion of the electrophile assists in the removal of the leaving group. The mechanism leads to retention of configuration at the reaction center, that you have R MXN, where R can be methyl, ethyl, etc. M is the metal atom and it is being reacted with En, where En stands for the electrophile with suitably placed nucleophilic site. So, N is representing the nucleophilic site here, E is the electrophilic center in this reagent. So, this will be forming this particular transition state. As you can see here, this R M X N, M being the electrophilic center gets attached to the nucleophilic center of the reagent, and R being electron rich will get attached to the electrophilic center of this reagent, and this will ultimately rearranged and the cleavage from here will take place and you are getting Re with NMXN. In this mechanism, you can see the internal assistance is being provided by the electrophile, which locks the backside attack of the electrophile, and thus it is similar to the Se2 front mechanism. Sci reaction proceed with retention of configuration. This you should always keep in mind. Now, after having a brief preview or a recap of the Se2, Se1 and Sci mechanisms, let us now see how the various factors affect the reactivity of these electrophilic substitution reactions. Among the factors that influence the reactivity of aliphatic substitution reactions, the nature of substrate, the nature of leaving group and solvent characteristics are the most important factors, and let us discuss them one by one. First of all, let us begin with the effect of substrate. Now, if you look at the effect of substrate in Sc1 mechanism, the Sc1 mechanism readily takes place with substrates having electron withdrawing functional group, that is by -M and -I effect. This is because the electron withdrawing substituents will stabilize the carbanion intermediate, which is formed in the Sc1 mechanism we have just now revised. For the Sc1 mechanism, the expected reactivity of alkyl groups is the methyl is most reactive, followed by ethyl, then followed by propyl, then followed by isopropyl, and then followed by neopentyl. So, you can see as the bulkiness is increasing, the reactivity is decreasing. Furthermore, it is a carbanion intermediate, so that will become less and less stable as you have these larger alkyl groups. Further, the reactions are possible at strained bridgehead carbons, unlike the SN1 reactions. And for Sc1 mechanisms, the electron donating groups will destabilize the carbanion and thus decrease the rate of reaction. Now, looking at the effect of substrate on Sc2 mechanism. For the Sc2 back mechanism, the reactivity order of alkyl groups is methyl followed by ethyl, then followed by propyl, then isopropyl and neopentyl, that is with the methyl being most reactive, and as the bulkiness is increasing, the reactivity decreases. Again, this order is followed as the backside attack is significantly affected by steric hindrance, and thus the bulkier the alkyl group, the slower will be the rate of substitution and thus reactivity. But for Sc2 front reactions, there are strong effects of substrate structure on kinetics. Experimentally, it has been determined that the branching at alpha carbon increases the rate of reaction due to electron donating inductive effect or R groups that stabilize the electron deficient transition state in the Sc2 front mechanism. On the other hand, branching at beta carbon decreases the rate of reaction significantly due to steric hindrance. Sc2 front reactions are possible at sterically crowded positions such as bridgehead carbon or neopentyl systems also. Now let us move to understand the effect of substrates on the Sci mechanisms. Unlike the Sc2 mechanism, where a relatively more electrophilic cationic mercury complex such as HgBr2 is advantageous, for the Sci mechanism a weakly ionic reagent such as LiHgBr3 is more suitable. The rationale being the extra bromide ion in LiHgBr3 would decrease the ionic character of transition state and act as an assisting nucleophile for the Sci mechanism. Now after going through the effect of substrate, let us look at some specific examples of the effect of substrate structure on the rate of reaction. Keto-Enol Tautomerism is an acid base catalyzed reversible Sc1 reaction that occurs in substrate containing carbonyl groups attached to a sp3 hybridized carbon bearing one or more hydrogen atoms. Thermodynamically, the keto isomer is more stable than the enol tautomer. However, based on substrate structure, in some cases the enols also have been isolated and even found to dominate at the equilibrium. This table, as you can see here, summarizes the key trends for keto-enol equilibrium constants for different substrate, and as you can notice here, for simple alkyl ketones and aldehydes there is a very small fraction of the enol present at the equilibrium. So if we take them one by one, here this K equilibrium constant K is representing the ratio of enol form is to keto form. So you can see for the compound this acetone, the equilibrium constant is 6.3 into 10⁻⁸, and as it goes to this 2-butanone, this value goes to 5.0 into 10⁻⁹. Then for 3-pentanone this value is 1.6 into 10⁻⁸. For acetaldehyde it is 5.0 into 10⁻⁶, and for this 2-methyl propanol it is 1.6 into 10⁻⁻3. Similarly, the other values are for cyclopentanone. So as we further continue looking at cyclopentanone, it has 6.3 into 10⁻⁸ value, cyclohexanone has 2.0 into 10⁻⁶. So it is now correspondingly the value you can see is getting increased, and when we go to this cyclic system having these double bonds in conjugation and there is a NH also in conjugation with carbonyl, and when it goes into enol form you can see it becomes aromatic, which is highly stable. So this value has significantly increased to 1.1 into 10⁻⁻3, showing the enol is more as compared to the keto form. Similarly, if you look at acetophenone, the value is 2.0 into 10⁻⁷, but when it goes to, we have two ketones which are in a position where the enol form, the double bond will be conjugated to another carbonyl, then it has again increased to 3.2. And similarly, here you can see when the carbonyl is in joined to CH2, further joined to the ester group, then because of the electron withdrawing nature of ester, it will help the enolization, and the enol form, the double bond will be conjugated to this carbonyl of the ester. So here again the value is quite high and representing the higher enol content. So in diketones we have seen here the enol form becomes significant fraction at the equilibrium, and this is because you can say the creation of a conjugated pi system and the formation of an intramolecular hydrogen bond that stabilizes the enol form. Phenol and other enols within the aromatic rings also exist nearly exclusively in their enol form in order to preserve or retain their aromatic behavior. In another example, when a carbonyl group containing molecule has two different R groups with alpha hydrogen atoms, there are two possible enolate structures that may form. In such situations, reaction conditions such as temperature and base usually control which enolate will be formed. Thermodynamically, the more substituted enolates are the favored products. However, if a bulky base is used at low temperatures, it would abstract the least sterically hindered alpha hydrogen, which leads to the less substituted double bonds in the enolate being the major product, and thus kinetic control prevails. For example, with the same substrate, the use of strong and bulky base LDA, that is the lithium diisopropyl amide, at low temperature yielded 84% of the less stable kinetically controlled product, while the use of triethylamine as the base at ambient temperature gave around 87% of the more stable enolate, which is the thermodynamic controlled product. So, this you can clearly see from these equations, that is the first case you are getting 87% of this E and Z, and in the other case it is the reversal of the product which is formed. So, you can see this difference in these two equations clearly. When you use the triethylamine as the base, then the percentage shown here, the terminal enol formed is 13%, and at the second position it is 87%. On the other hand, when we use LDA, then the terminal enol is in 84%, and at the second position it is 16%. So, almost a reversal which is happening. Effect of substrate structure on alpha halogenation of ketones, if we try to study, let us go into the details of this. The alpha halogenation of ketones is an example of Sc1 mechanism that involves a carbanion intermediate. The major product obtained upon alkylation of the enolate formed by the reaction of lithium diisopropyl amide with 4-tertiary butyl cyclohexanone is the trans isomer. The cis product is the thermodynamically more stable structure because the R group would be in equatorial position instead of axial position. The reaction proceeds via a chair-like conformation of the enolate when attack on the top face takes place, leading to a transition state with the ring still in a chair conformation. On the other hand, attack from the bottom face leads to the ring into a boat-like conformation, as you can see here. Hence, the trans product dominates due to the lower energy chair-like transition state, and thus depending upon the nature of substrate, different product is obtained. After the effect of substrate, let us go into the details of the effect of leaving group on these mechanisms. For unimolecular as well as bimolecular electrophilic substance, good leaving groups enhance the rate of reaction. In general, the electrophilic substance requires an electropositive leaving group attached to alkyl group substrate. In the aliphatic organic chemistry, most of the functional groups are electronegative. Therefore, due to the lack of substrates, the number of electrophilic substitution reactions is less as compared to nucleophilic substitution reactions. For Sc1 mechanism, the formation of carbanion is the rate limiting step, and therefore good leaving groups will enhance the rate of reaction significantly. The polar CX bond makes it easier for the leaving group to leave. Although a number of reports on Sc1 reactions with metallic leaving groups have appeared, but the mechanism has not been proved, and generally carbon leaving group favors the Sc1 mechanisms. If we talk about the Sc2 reactions, the Sc2 reactions proceed with alkyl groups attached to metals as leaving groups. Organomercury compounds have been most extensively studied for Sc2 reactions as they are stable and sufficiently reactive. For the substrate RHgX, the more electronegative group X decreases the polarity of CHg bond and hence results in a less stable HgX positive. Therefore, leaving the tendency of HgX decreases with increasing electronegativity of X, and thus we can compare that HgR is a better leaving group than HgCl, which is obtained from RHgCl. Now, let us move to the effect of solvents. There are considerable effects of nature of solvents on Sc1 mechanism. By changing the solvent, products with retention of configuration or inversion or complete racemization have been obtained. Between the competing Sc1 and Sc2 reactions increases the possibility of an ionizing mechanism and thus favoring the Sc1 in comparison with the second order mechanisms. The role of solvent has been also established to exert an influence between the Sc2, that is front or back mechanisms, and the Sci mechanisms, in that the rates of Sn2 mechanism should be increased by an increase in solvent polarity, while the Sci mechanisms are much less affected. If you look at the effect of solvent on Sc1 mechanism in detail, for the cleavage of alkoxide through Sc1 mechanism, depending on the nature of solvent, different product stereochemistries were observed. These results are explained by a carbanion intermediate that is not completely free but is solvated, as you can see here. So, you can see here this anion, and it will be undergoing removal of this R, and you have the formation of RH and this ketone. So, here for example is this group, that is PHCMeCt. So, this will be the tertiary carbon which will be attached to this carbon. For the reaction, the nature of base and solvent influence carbanion stability and extent of solvation, which eventually determine the stereochemistry of the product formed. In protic solvents such as diethylene glycol, inversion of reaction center was found to take place, and this can be exhibited like here. So, you can see here that in presence of diethylene glycol will be forming the hydrogen bonding, and it will be affecting here. So, this is because in polar solvents the leaving group solvates the carbanion, and the solvent can solvate it only from the opposite side when the CH bond formation occurs. For the reaction, the nature of base and solvent influence carbanion stability and extent of solvation, which eventually determine the stereochemistry of product. In protic solvents such as diethylene glycol, inversion of reaction center was found to take place, and as you can see in this mechanism shown, that this is because in polar solvents the leaving group solvates the carbanion so that the solvent can solvate it from the opposite side when the CH bond formation occurs, and this results in the inversion. In polar aprotic solvents such as DMSO, racemization was observed to take place for the reaction, and this is as in aprotic solvents the carbanions are relatively long lived, as the solvent has no proton to donate. In non-dissociating non-polar solvents such as benzene or dioxane, the alkoxide ion exists as an ion pair. It is solvated by the solvent BH as shown in this schematic diagram. You can see here, and from this it is clearly apparent that the solvation is asymmetrical, since the solvent molecule is already on the front side of the carbanion, and when the carbanion actually bonds with the proton, the result is retention of the original configuration, and thus overall solvent plays a very important or a major role in controlling the stereochemistry of the product formation. Now, moving to the effect of solvent on the Sc2 mechanism in detail. For the bimolecular Sc2 mechanism, in order to determine the various factors influencing the isomer distribution, small samples of cis and trans mercury compounds were cleaved with different brominating agents under a variety of conditions for some reactions that will consider. So, let us take this equation where the cyclohexane is attached to methyl and HgBr, and when it is brominated, then you can see in place of HgBr the Br comes, and the results obtained in a variety of solvents for this reaction is tabulated as shown here, and the solvents like CCl4, CCS2 or acetic acid, variety of them were used, and the environment was of nitrogen or air. So, this table is depicting that how the percentage of cis and the trans product is varying, and in terms of retention in the stereochemistry it is also mentioned, that is, and you can clearly see here that in non-polar solvents such as CCl4 and CS2, both isomers yield the identical mixture of cis and trans 4-methyl cyclohexyl bromides. In more polar solvents or solvents containing a trace of alcohol, the reactions were found to occur with partial retention of configuration. Under these conditions, the addition of air to the reaction vessel resulted in a marked increase in the amount of retention. However, in pure carbon disulfide as solvent in the presence of air, complete inversion was found to take place. Overall, the nature of solvent influenced the product stereochemistry to a great extent for this Sc2 reaction. So, dear students, let us now summarize what you have learned in this module. We have quickly recapitulated the electrophilic substitution reactions, that is, they are the reactions where an electrophile replaces another atom or group of atoms on the substrate. We also discussed that how the Sc1, Sc2 and Sci mechanism operate. Sc1 reaction follows the first order kinetics with respect to the substrate, whereas the Sc2 and Sci mechanisms, they follow the second order kinetics. Sc1 mechanism readily take place with the substrate having electron withdrawing functional groups, and for the Sc2 back mechanism, the reactivity order of the alkyl groups, you should remember, is methyl is more reactive, then ethyl, then propyl, then isopropyl, then neopentyl, that is, as the bulkiness increases, the reactivity decreases. For Sc2 front reactions, they are possible at sterically crowded positions such as bridgehead carbon or neopentyl systems also. We also studied that how the Keto-Enol Tautomerism is an acid base catalyzed reaction involving Sc1 mechanism, and for simple alkyl ketones and aldehyde, there is very small fraction of the enol present at equilibrium. We also studied that depending on reaction conditions such as temperature and nature of base, the kinetic product may predominate in electrophilic aliphatic substitution mechanism. For unimolecular as well as bimolecular electrophilic substitutions, the good leaving group enhance the rate of reactions. The polar CH bond makes it easier for the leaving groups to leave, and between the competing Sc1 and Sc2 reactions, an increase in solvent polarity increases the possibility of an ionizing mechanism and thus favoring the Sc1 as compared to Sc2 or Sci. The rates of Sc2 mechanisms can be increased by an increase in solvent polarity, while Sci mechanisms are much less affected.